prospector in the known universe. He's been busy here at the conference communicating with his colleagues at NASA in support of a deep space mission now. He can tell you more about that later, but since we're on a very tight timeline and we're a bit behind already, let me have Professor Ahern take the podium and begin the session. Thank you.
We'll have slides soon. This session, we've taken two people from the science side who purport to know what's out there, and used them to bookend two people from the mining side who know how to get out what's out there. And I hope that this will be the right balance for this session. My own talk will be rather short in hopes of keeping the session, getting us closer to back on time. And I want to hold all the questions until the end, as was done in the morning session, the previous morning session. I think that works better to have all four of us up here for unified questions. Okay, now we actually have my presentation. My real experience is with comets, although I have done a moderate amount of work on asteroids as well. I want to make a distinction between when we're looking for resources because we need them back here on Earth, or resources that are needed for exploration, i.e. we need resources in space. Because what I really want to start talking about is NEOs, and in particular, I'll talk about the ones that provide a lot of water, which is a resource that makes sense to bring to space from space, rather than having to get out of large gravity wells. Because a large gravity well of a planet, even moon, the gravity well is a significant effect in trying to get resources into space. Faith will talk more about the rocky things. Go to an NEO, you have a longer return to the vicinity of Earth than you do from the moon, of course, but it's less than or comparable to what you have to do to get back from Mars, and certainly less than what you have to do to get something back from the main asteroid belt. You also can, of course, take the resources to somewhere else in the solar system, or wherever you need them, and move them around. Here's one example of a paper that's been written about. I don't know this fellow very well, but I've been off and on communication with him for 6 months. He's identified a particular asteroid, 2006 WB, not a well-known asteroid to most of us, but it is it's like Apophis. It comes very close to the Earth, so it's good for capturing into Earth orbit. And he's developed a whole scenario for putting it into Earth orbit, using it as a rotational mass driver, using the spacecraft to build up angular momentum, and then using that to eject other things. And he proposes bringing the expensive things, the stuff that's valuable on Earth, which is more or less a byproduct, down to Earth to be sold commercially. I don't know the taxonomy. I don't know what type of asteroid this is. Faith may know, but she's shaking her head no, she doesn't either. I don't really want to talk about this one. I want to talk about a specific subset of near-Earth objects. There are lots of different types of near-Earth objects. Most of them are predominantly rocky and/or metallic. But about 15% of them are very low albedo, and they're in what we call cometary orbits. For the one or two aficionados in the audience, that means Tisserand invariants less than 3. For everybody else, that's just jargon. It means they're like Jupiter family comets or Halley class comets. So 15% of the NEOs fit into that category. That's more than is predicted by the models. The models predict that only 7 or 8% of the near-Earth objects should be like this. But factors of 2, if it's astronomer, you're worried about factors of 2 if they're in the exponent. Some of them, a few of them are real comets. Comet Bachmann 3, which is broken up. It's got somewhere over 80 pieces now, all in independent orbits. And several of those are potentially hazardous objects, i.e. they have very close approaches to the Earth's orbit. But I'm not going to talk really about the hazard issue, but about the resource issue and what resources are there and how you get them. So the biggest resource in a comet, and although most of the others are not comets in the sense that they're outgassing and releasing water, they are almost certainly dormant comets with the ice sealed inside just by a thin crust that has managed to, a lot of the organic material has managed to seal off the vaporization. Half the mass in a typical comet is water. So this is not a trace species that we're looking for. If you want hydrogen and oxygen, it's half the whole body. So that's good. We'll have to come back and ask this question, where in the body is it? Is it in the center, on the surface, mixed throughout? And we're not sure about that. I'll come back to that question. Also, a lot of organics. Carbon to oxygen ratio in comets is roughly the cosmic abundance. About half of that is in carbon monoxide, carbon dioxide, methanol, a few basic species like that, and about half of it is in what's called CHON. These are the mysterious particles that were discovered on the Vega and Giotto spacecraft at Comet Halley. Basically, refractory particles that you have to hit at 80 kilometers per second to vaporize them. But the only atoms that come out then are carbon, hydrogen, oxygen, and nitrogen. So they're organic stuff. Organic stuff that does not evaporate at 300 Kelvin. Nitrogen is strongly depleted in comets relative to the cosmic abundance. There are also minerals there. We know there are silicates of various types, but we don't know a lot about the mineralogy of content of comets. Where's the ice in comets? Those arrows point to places on the surface of Comet Tempel 1 where we found ice 5 years ago. Actually measured the ice there. Total area, so those really bright areas that it's pointing to really are bright. They have a reflectivity of about 6%. That's slightly below charcoal briquette. And those are the bright areas. Those areas are covered by about 3% ice. And the total area of those areas, they're slightly bluish in color, which is how we recognize them. Subsequently, we took spectra of them, and we really see the ice absorption bands. Total area of about half a square kilometer with 3% ice. So that's not very much ice on the surface. And in fact, that ice is absolutely irrelevant to where most of the water comes from. But most of the water doesn't come up there. Some does. The subsolar meridian, noontime, is about here. And right over here is where you see all the water. And we map the water that's coming out with our spectrometer. And it's all coming out over here. Consistent with all coming out within an hour or two of noontime. So, where is that ice? That ice is certainly near the surface, but not on the surface. If it were as much as 1% ice coverage on the surface, we could have measured it easily, just from knowing how well we measured this ice up here. So there really is essentially no ice on the surface down here. Right about in here is where the deep impact went in. That excavated 5,000 tons of water. So we've actually done the first mining experiment. Now, We didn't have a business model, so we excavated the stuff, but we didn't have to deliver it anywhere. So we've only done half of the experiment, but it is a step in the right direction. It put it associated, we had 5,000 tons of hydrogen and oxygen, fully separated, over some huge volume. I leave the engineers to figure out how to collect it. So here are just two movies to remind you of the deep impact experiment. This is the view from the impactor as it's going in. You notice it bouncing around like that? That's a 1/3 of a ton impactor being bounced around by 1 milligram dust particles. 1/3 of a ton being bounced by milligram particles. That's because of the high speed. We're going in at 10.3 kilometers a second. On the right-hand side, that movie isn't playing very well, but it is playing. That's the view from the flyby. And you see all of the material, well, it's going to start over. You see all of the material expanding into space. The water dissociates on average in a time scale of a day or so. At this distance from the sun, a day and a half. Dissociates into water, into hydrogen and OH, and then you have to subsequently dissociate the OH, which takes several days. So the material is gone forever. But that experiment excavated ice. Didn't excavate water vapor, it excavated ice. And we know that the ice had to be within 2 meters of the surface, just from the spatial distribution and where it came out. Within 2 seconds of the impact, we saw ice in the ejecta. So it's very near the surface. Getting it all, that vaporized all but spontaneously at noontime suggests that it's probably within 10 centimeters of the surface. So it's very close to the surface, or at least some of it is. We know nothing about the 3-dimensional distribution of water versus the rocky stuff and the organic stuff in the interior. We don't have enough data to resolve that question. So we have some data, but not a lot. Okay, so one way to return the resource is actually to move it. You wouldn't want to move Temple 1. That's 6 kilometers in diameter. That's a bit heavy to move. But most of the near-Earth objects are a lot smaller than that. The comet-like NEOs are much smaller than that. So much smaller than the ones you can think of moving. We were consciously going to a big one to be sure we could hit. Because the resource you're after is water, the bulk of it, returning the whole bulk of the body is a very efficient process. And we have indirect measurements of half a dozen other comets that give you similar numbers. So you're mining in incredibly porous stuff. Now, that's canceled out to some extent. You won't actually sink into it because there's zero gravity. The escape velocity is 1.5 meters per second. You can actually walk off the body. You don't need a running start. You know, people with good health can walk 1.5 meters per second. I used to be able to. So you have to keep that in mind. The material is incredibly weak. These are basically, whoops, that's not what I wanted. Tensile strength on a kilometer scale is less than 100 pascals. That's something like 5 orders of magnitude weaker than coherent ice. From deep impact, at meter scales, we have an upper limit of 10,000 pascals. That's still 1 to 2 orders of magnitude weaker than completely fractured.
Aerospace engineers over the years have been starting to think about things. It's kind of cool. It's interesting too, which is strange. All right, mine development, site preparation, that's a kind of a precursor, extraction and transportation, orbit modifications. Again, you're back to astrodynamics. Asteroid miners are going to be a combination. The guys that really can make this stuff work are going to be some kind of hybrid between mining engineers and astrodynamicists, really. Because if you don't understand principles in terrestrial mining. We want to maximize productivity and revenues. And again, these may or may not map to asteroid mining. Minimize costs and the needs for reclamation, because that's a long-term cost, cleaning up the mess. Actions that lower risk are typical. Okay, you'll often see where it's very difficult to sell a mining company on a new technology that works better because the stuff they're using is relatively low risk. They understand the risk profile. So mining is actually a very risk-averse industry, and which is why asteroid mining may be a stretch for that. So it's a new hybrid is needed. Mining design process, planning and sequencing of unique operations in time in three-dimensional space. How do you scrape off the bad stuff, get to the good stuff, and deliver it to your customer, and do what you need to do to make it add enough value in it to maximize your profit along the way. Keep going. So how do you extend this? If I'm going to talk about mining methods for asteroids, we've got various mining methods for Earth ore bodies. You got blockading, you got various types of stoping. There are ways that we fall into certain categories of the way we do Earth mines. And basically, like trying to reach out of the air and extract some of what I've seen in the asteroid mining community and the published literature, some insights into maybe naming some new mining methods, which is the next slide. And pardon my sense of humor here, but I'm trying to be creative. This is sort of the process of classification. If you want to look at what's kind of been out there for a while, put a mylar bag around it, increase insulation, start reflecting some of the infrared back on the asteroid. You can slowly increase the heat as all the holes are created. You begin to accelerate that process because the conductivity does raise. There's a magnetic rate concept, for chondrites that are poorly mixed, I guess, where you can get the high grade magnetically susceptible nuggets with supposedly higher grade platinum results in them. Take a small piece home, kind of like this one for asteroid sample return. You might be able to actually return an industrial size sample of an asteroid with current technology. I think that's a pretty good idea, and maybe something that human mission might want to look into. New moon, captures, put it in Earth orbit. This is dangerous. This scares the heck out of the planetary defense people. They're trying to keep this from happening because what happened if you miss. Hot knife, Tony Zaparo's idea with nuclear heat. 95% of the mass of your nuclear reactor is in space is getting rid of the excess heat. Mosquito, remove the good stuff. Laser torch. So operational experience will determine which method works better. And then here's some pictures of some of these types of methods I've scattered out of the literature. Again, this is hypothetical stuff. This, by the way, is from a game online, multiplayer online game that they do, whatever it's called, E. And these kids love asteroid mining, partly because their income or whatever it is on it. But the mining lasers, as an engineer, I find that hard to implement. Unit operations. This is a concept within the mining industry of kind of talking about. It breaks the mining process down into individual units of operational activities. And I think the con-ops and unit ops concepts I think are pretty close here. The concept of operations that the aerospace industry people use. So I think this is a good match. Again, it's another taxonomy issue. But there's a lot of literature out there that talks about rendering operations. Capability analysis. This is really Jerry Sanders over there. If you can raise your hand real quick. Jerry's was the lead on our ISRU capability roadmapping team several years back. It looked at mostly lunar stuff, and under Jerry's leadership, a large team of people kind of came up with a list of capabilities that are required to implement lunar and Martian research. And I think that most of that, 95% of that maps over to the asteroids. And again, it's an extensive amount of work. A couple hundred page report came out of that, and at least my group was also involved. The difference between technologies and capabilities is pretty significant. Several technologies can be applied. Drilling versus, it's like we've actually done this one, so we can write those samples on Mars. And according to drilling, we don't have any Apollo astronauts here that did that on the moon, but that's been done. Grinding, this is the honeybee rat tool that was used on Mars to get a fresh surface to do X-ray fluorescence. Mars atmosphere capture and separation by the coolers. We have some of these capabilities. It's you know, in-space demos, and we should definitely acknowledge that we're making progress. And right now there's what I guess a remote bombing of a comet, explosives research in space. So you know, there's more. And the terrestrial mining industry is Greg Baden over there, a lot of semi-autonomous, is one of the leaders in mining automation. There's you know, production rates are relatively high. There's a lot of history and heritage. The mining industry is actually implementing some critical technologies. There's enough mining people in the audience here that can get you in touch with some of that if you guys are interested. Okay, so this comes directly from one of Jerry's slides, mostly modify that and talks about capabilities and taxonomy. We have gaps and risks that are associated with that. And synergies. Let me get to the planetary defense stuff. I kind of like the flood control analogy, where the Army Corps of Engineers will come in and they'll build a dam to avert the 100-year flood or turn it into a resource for a local community. Rather than every 100 years the flood comes through the valley, wipes all the farmhouses, you turn it into a reservoir, you can do naval boating, you've got hydroelectric power generation. So the government comes in, maybe in concert with a public-private entity or some kind of private corporation that then turns this problem, this hazard, into a resource. And I think the planetary defense strategy of activating asteroid mining for human space enabling that, I think it's a win-win kind of strategy. Asteroid mining could be used to de-threaten the PHA. That's basically the point. In other words, depending on how you're doing that. This is from one of the less inspired papers where they looked into this, how to do it, and again, it's a taxonomy based on size and composition, and then looking at the types of explosives that would be needed to modify the orbit of an asteroid. But this comes from mining industry experience with explosives. All right, conclusions. I think it's a good idea to partner. We think it's a good idea to partner with planetary defense folks. I know Pete Garrison pretty well, and I think that's pretty much the way that we stand forward. Until the U.S. actually develops a planetary defense office, I believe right now the current status is that there's a planetary defense subcommittee of the NASA Advisory Council, and the progress is being made. Still steady within the government. Problem is that unfunded liabilities. Where do you get money? If you give somebody a job, in the Air Force or within the National Security Space Office or whatever, where's the money going to come from to implement that? And some of that may actually basically a public-private partnership means that you can actually get some private money to help do that. So it's a win-win situation. This is motivational. Hopefully that's where we're going. Any questions?
Unless there's a really urgent one, questions will
I did see one.
Sonter from Asteroid Enterprises. And we'll be talking about mining concepts.
I was interviewed last night as a mining engineer. I'm not a mining engineer. I'm a physicist who has worked in the mining industry for 35 years. I'm a physicist, and that means that I really can't find it. Okay, fine. Why is that? preserving and expansion of the solar system. The technologies to tap these resources will also enable the deflection of at least some of the impact threat objects. It's likely that NEAs will be major resource plays for the mid-21st century. Therefore, we should seek to develop them with all due speed. There's a high and increasing discovery rate of near-Earth asteroids. I'm using NEAs and NEOs interchangeably, so please excuse me, and Mike, you're the one that just reminded me by your conversation that should be NEOs to be more general. When I first started looking at this, there were about 350 known NEAs. There's now something like 8,000 and growing rapidly. And as I think Coyote said sometime in the discussion last night, that with pan stars coming online, there's going to be a huge flood of extra targets being found and identified. There's a growing belief that NEAs contain easily extractable products. Accessing asteroid resources is dependent on development of markets for mass in orbit. People talk about bringing PGMs back to Earth, and I'll show later on why I think that is a sideline issue. Somebody else, I can't remember who, said that platinum group metals will only ever be a byproduct, and I think I can prove that categorically. A question that's been exercising my mind for a long time is how do you compare different schemes for mining an NEA and returning the product to market? And the answer partly has to be that economics is a design driver. Economics is a driver of how you make your choices. CapEx, capital expenditure, payback time, net present value are critical design drivers in choice of the targets, in choice of the market, the product, the mission type, the extraction process, and the propulsion system. The thing's got to be economic, it's got to be able to pay its way, otherwise it won't fly. So here's just some numbers as of a couple of weeks ago when I was going through them. Total number of NEAs, NEOs now is of the order of something like 7,200. About 3,200 of them greater than 300 metres in diameter, about 800 of them greater than 1 kilometre diameter, nominally. And potentially hazardous asteroids, the numbers there, 1,100, 500, question mark, that's my guesstimate, and 150. And there's the split up between the Apollos, the Angels, the Athens, and apparently the inside of the ones are now called Asteroids. Although I do remember Arjunus was the name that it has to start with a name. What's the name of the fellow that started Space Watch? Tom Gerrels, thank you very much. Tom Gerrels called them Arjunus. Here's some pretty pictures, and we won't dwell on it except to say there's a really interesting zoo of different categories and properties and queries about how you might mine them. Utilization is close in size to a likely mining target. It's been found as a rubble pile with lots of void space, bulk density 1.95 regolith, gravel-sized particles. We now know asteroids retain deep regolith. That was unexpected. They're often heavily fractured or rubble piles, significant void space. Many appear to contain water in clays or salts, and angle and nickel iron and PGMs. Some may be thick comet cores, and Michael just talked about that. Products, well, we've talked through that. There's the listing. Water is an obvious first product because it can be used for propellant for the return trip to bring the material back to market. Now, I'm going to do a number of comparisons with terrestrial situations, and this parallels a bit what Brad and Leslie were talking about. In terrestrial mining project development, this is the sequence that companies or prospecting people need to go through. First of all, they start the desktop study where they decide, they being the prospecting company, what commodity to look for and where. It might be copper in Chile, or it might be uranium in Kazakhstan, or it might be gold in the Nevada Carlin Trend, or whatever. So what do we want to look for and where? Open literature, proprietary data reviews, look at information in geological survey libraries, look at PhD theses and things like that to try and zero in. And you end up with a series of prospective target areas that have been identified, and then you can measure constants, on-ground constants. Identification of targets. targets within those protected target areas, and then finally field work, hopefully, identifies first of all some mineralisation and extended mineralisation, and that triggers the first big spend of money where you start drilling out your potential ore body. Metallurgical work, okay, so now you've defined an ore body, metallurgical test work to confirm extractability, and then you're getting more and more comfort that you know that there's something there. It's big enough to mine, it's a high enough grade to mine, you know how to process it, it's beginning to firm up in terms of a concept. So you move to the next stage, which is the project conceptual planning, pre-feasibility studies, and finally the bankable feasibility study and environmental impact statement, and let you go to the bankers, get your loan, project go ahead, construct and commission. And with any sort of luck, the commissioning contractors end up giving you a project that's more or less nameplate capacity, more or less on time, more or less on budget, and more or less performs. Maybe. And there's lots of cases where it doesn't. So, material is ore only if you can mine, process, transport and market it for a profit. Terrestrial mine project planning involves choosing between competing mining and metallurgical extraction concepts to minimise capex, minimise OPEX, minimise payback time, minimise project risk and thereby maximise the expectation net present value. You've got to have the same mindset in space. Bankable feasibility studies have to develop a mining plan based on an accurate ore body model and a metallurgical process flow sheet based on accurate understanding of the ore, which maximises recovery and succeeds in achieving those things I listed on the previous slide. There have been plenty of cases where the ore body model was incorrect and the mining company started mining and then discovered to its horror halfway through, or a few years, 2 or 3 years down the track, that it was missing a lot of its ore. Sometimes this cruels the project, sometimes it merely diminishes the potential return. There have been cases where projects have been held back for decades because the metallurgical flow sheet could not be developed that would give adequate recovery. So choice of mining plan and process is often surprisingly difficult, even in terrestrial situations. I've been involved in these 4 projects and others in Australia, and Olympic Dam is Australia's biggest underground mine. I saw it grow from nothing, from an initial shaft sink, a copper uranium gold project, and we did not know how to mine this thing at the start. It was obvious from the very start that it was a big, big ore body. And it's the biggest uranium ore body in the world by a factor of 4 or 5 or 6 or 10 or some unknown amount. But we didn't know how to mine it. Very, very first look was, can we open pit this thing? Well, it's half a kilometre underground to skylight the ore, and it would have cost a couple of $1 billion back in the early 80s to do that pre-strip, so that was perceived to be impossible. Different underground mining methods, vastly different underground mining methods presented themselves, and we have to winnow down by a long, thoughtful process, an iterative process. Guess what? Now, after running for 25 years, the company that owns the project finds that it literally cannot increase the output from it via underground means, and they're again looking at open pitting it. There will be a huge open pit if they go ahead, but open pitting is seen as the way to remove this constraint in getting stuff out of the ground. Mulga Rocks is a uranium base metals rare earths project where it's still in the feasibility stage, and my colleagues are going through how do we mine this beast. It's several layers of uranium, nickel, cobalt, scandium, etc., at different depths. Major pre-strip problem, major waste control problem. How do you do it so as to get what you need out? The Nolan's Rare Earth Project, major challenge. Easy mining, it's all on the surface, but the challenge there is getting the process right. Very refractory material, you concentrated caustic bleach, concentrated nitric acid bleach, concentrated oxide, and that's talking about concentrated sulfuric. Difficult processes. The Beverly Uranium In Situ Leach Mine was one where they thought they had an accurate ore
model. It was originally going to be an open pit. It's now become an in-situ leach. It's been running for about 10 years. 2 years down the track, they found they were losing something like half of the ore because they didn't understand the layout of the ore underground. And once it was lost those areas, they had to go and do much more careful identification of what was where. The implication of the economic imperative for asteroid mining, in order to maximise your NPV, your net present value, you need to minimise project risk, you need to minimise the capex, and that implies unmanned, small remote miners in my vision of the thing. Maximise the return payload fraction, that means minimise return delta V, and that means you've got to try and identify easy to get to and easy to return from objects. Including capture, lunar capture of the return package is a potential big enabling factor. Minimise payback time, that means you don't want to be sending something out on a long return mission because the time value of money kills you. Asteroid mining projects will be driven by those items. There's a crypto comet model, and Mike was talking about comets and question, how do you mine these things? Well, some of us knew a fellow by the name of David Cook who looked at the idea of basically black light underneath the skin of the comet and pulling out the volatiles and condensing them. I had a look at that idea, and we looked at surface reclaim, we looked at solar bubble, in-situ volatilisation, explosive excavation, downhole jet monitoring, and ended up deciding that many of them were not robust enough. The blowout risk was high, or the loss of fluid, loss of circulation was a problem, and I ended up going back to underground mining by mechanical mould. That's a very poor diagram. I apologise, but there's the idea of a collar, a drill, access hole, and a mechanical miner digging out a void at depth. Rubble pile model is what we seem to be seeing now in terms of asteroids. How do we mine this thing? Well, all I'm doing is presenting ideas. A mechanical model of some sort to cut, grind up. You're going to need ground control even in micro-G. Ground control is control against collapse. Right? Containment of cuttings, transport of cuttings, and process plant separation and storage. I'm going to quickly flick through some comparisons with terrestrial mining, but I want to make the point that comparison with large, low-grade, high throughput, low margin commodity operations is not the way to go. Our comparison with the terrestrial situation should be remote, high grade, very high value, very high margin, very small throughput, exotic product operations. That's the Kalgoorlie Supermine in Western Australia, 100 years of gold mining, not a useful comparison. The only thing to take away from this thing is the value of ore at today's gold price, about $140 a tonne. Terrestrial remote high value mines. A Canadian diamond mine in Canada, accessed by ice road 10 weeks a year. Namibia offshore diamond region, Scotland coast. Garimpero illegal gold mines in Brazil and elsewhere. Bololo gold mines in New Guinea in the 1930s. More air freight was flown than the entire rest of the world total to build. I've got 3 there, but I turned out to find out it was 8 1,200-tonne dredges in the period 1931 to 1935. And I've got a couple of pictures later on. Port radium in Canada. Radium in the 1930s was $50,000 a gram. And pure pitch blende ore that they got the radium from, pure pitch blende ore, came out something like $10,000 a tonne. North Pacific deep sea massive sulphides, Gary? Yes, Gary's been involved in that thing, and I'm fascinated by the potential comparisons with asteroids. Pictures. That's literally true. Those villagers were panning for gold and flagging down helicopters to take them to the bank. Antarctica fields in Australia's mad native country. These are the dredges that were flowing in these three-engine junkers. They had the roof cut out of them, and they carried building materials and built 3 hydro power plants and 8 big dredges to get to the gold. That's where it was, in there, 50 kilometres from the coast. So there's a vast range of ore in situ leach, metallurgical flow sheets got to be correct, otherwise you lose your project. Ore grade is not measured in grams per tonne or ppm or kilograms per tonne or percent. It's really measured in dollars per tonne. And surface commodity mines generally mine about $100 a tonne. What about asteroids? Well, if you've got an asteroid with 50 ppm platinum group metals and 10% water, guess what? The platinum group metals value is $4,000 per tonne of regolith. The water value is $1 million per tonne of regolith. If you're selling it at $10,000 per kilogram delivered into Leo. Is this all? Well, yes, but only if we can mine, process, transport, and sell at profit. 2 minutes, fine. Terrestrial mining, deep sea massive sulfides, metal grades can be plus 50%. Why deep sea massive sulfides? Lower discovery cost, low cost, easy trial mining, shorter development time, easy ore access. You don't have to build a shaft or a decline. No landowner compensation cost. You see there's some parallels with asteroids here. Cheaper beneficiation, easy metallurgy due to high grade, no pit to port infrastructure. Cheaper plane to build and ship out south site, move to market sites. So, comparisons with terrestrial. NEAs are prolific with subset having low delivery. Many are prospective for water and nickel iron. Very, very valuable ore. Easy extraction, question mark. Target return parcels maybe 1,000 tonnes. This is analogous to short campaign trial mining rather than large long-term mining. What will an asteroid mine look like? I don't know, but I think the answer will depend on the target ore body model, what we're after. I think it will be small, highly integrated digger plus processor, almost certainly reliant on in-situ propellant production for return, almost certainly solar powered. I'm assuming the first product is water delivered into LEO, GEO, or hydroelectric or Earth. And that is it. Thank you very much.
Sonter. Last speaker of this session is Vilas, the director of the MMT 6.5-meter telescope in southern Arizona. And he'll talk to us about the other 85% of the AOs and the astrophones.
I'm going to hope that I operate this correctly. If Mike is correct, I'm going to talk about the rest of the asteroids. I was invited to talk about mining asteroids, so I go a little bit beyond the NEOs, but that's okay with me. You better get this right. What do we know? First of all, the first question I asked myself when I was thinking about what do I want to tell people is how many asteroids are there to mine? And to that extent, I thought, okay, it's been 210 years roughly since the first asteroid was discovered. So this is sort of a progression that shows you how many asteroids we actually have known in what year. Earth-crossing asteroids are in red outside Earth's orbit. This is mostly the outside the Earth's orbit is green. This is mostly just the main asteroid belt that you're going to see. In 1800, we didn't know of any asteroids at all. By 1900, we began to see a few asteroids. By 1950, the main asteroid belt is beginning to be populated. You'll note that we have a few near-Earth asteroids, the ones in the red. We have all this looking roughly Mars and Venus, in this case. 1990, we're beginning to try to discover more and more of the near-Earth asteroids, and as a byproduct, of course, we're discovering more main belt asteroids. And now the projects of discovering asteroids are becoming more and more effective. 1999, you can see the number of near-Earth asteroids that we have, and then this stops in the year 2006. So this is what we roughly had in 2006. However, still learning my handle here. Yesterday, I went on the JPL Horizon site and noticed that we have 500. There are 861 asteroids for orbits that are well enough known at this point. 7317 NEAs. I will talk only about near-Earth asteroids. That's what I'm talking about, not NEOs. I've excluded the comets from the discussion. And of those, about 1150 PHAs. Generally speaking, the potentially hazardous asteroids are about 20% of the known near-Earth asteroids. The same percentage follows with the PHO-NEO connection, include the comets. An estimate we've got in the last couple of years is that there's roughly 66,000 plus near-Earth objects, and of those, 18,000 are potentially hazardous objects. Those potentially hazardous objects are objects that would come within 0.05 astronomical units of the Earth's orbit. That's what defines a potentially hazardous object, and a potentially hazardous asteroid is a subset. Anyway, this is what we're working with at this point. We've got a lot of objects out there that we could take a look at. So, what are their compositions? The first thing I wanted to talk about here is that we can approach this through different means. We approach it through the remote sensing of the mineralogy. Again, I'm not talking comets and tons of atmospheres here. We're talking surface rocks, mostly, or surface materials that are rocky. Mineralogy from a telescopic or spacecraft observations of the spectral reflectance. What is that? Which I'm sure you probably all know, but to remind those who might not. The sun comes out, hits the surface of the asteroid itself. It interacts with about the top 1 millimeter of material. That's affected by it goes inside, bounces around, comes back out, and is affected by the crystal structure of the minerals that are in that top millimeter of material. This seems like it shouldn't work, but we actually have first order evidence that this does work. The test of this was in the Apollo program, when before we went to the moon, we took a lot of telescopic images of spots and spectra of spots and determined that they looked like some types of minerals, and then we went to these locations, brought back samples, pristine samples from the moon, and learned that, in fact, the laboratory reflecting spectra of the samples was close enough to the telescopic reflecting spectra to show that this technique does work. Even with all the advances we have now for learning whether or not there are changes in the effects on surfaces of all these different types of objects, this still works. Even with asteroids, if you're looking at this 1 millimeter of material, you have first order evidence that there's differences in composition because you're seeing the differences in the reflected spectra. No matter what is affecting them, you do have differences. They probably are real. The question is, do we really understand them? Ground truth for asteroids are usually the somewhat contaminated terrestrial meteorite samples that we have. And they're all contaminated, no matter what, apparently. We also have spacecraft elemental compositional experiments, gamma ray, X-ray spectroscopy, neutron spectrometers that can look at elemental composition of the material that they're passing over. But that requires close proximity to the object that you're studying. So spectroreflectance probably gives us the spectra and photometry for which we can class the asteroids, use a classification scheme. But our spacecraft visited probably less than about a dozen asteroids. They landed on 2 asteroids, Eros and Itokawa, and possibly returned a very small, like in particle grains, samples of Itokawa of 1 NEA. This is about to increase hugely in the near future. It's going to increase, but not a tremendous amount. So Earth-based, and I say that meaning both from the ground or from space assets, Earth-based remote sensing is at present our best means of studying a large sample of asteroids, and that has some problems with it too. Now, I'm going to show you this. This is old. This came out of the 1980s. This is from an astronomer named Dave Foreman. The idea of classifying asteroids has expanded since this time, but this serves as sort of when everybody can't figure out what they're talking about, they back off and refer to Foreman's C classes, which are here, or the S class, or some subsets of these classes. And so I'll sort of use this as a back off and refer to it. The other thing about this that I think is still amazing is that this is a one man's doctoral thesis, and it still represents the core of this particular approach to classification of asteroids, and it stands the test of time, about 20 to 30 years right now. So the first of these I'm going to talk about, I marked in red, and I'm not going to talk about them a lot, but these are the sort of the S-class asteroids, the asteroids that look as if they're rocks. They're mafic silicates, pyroxenes, olivines, different mixtures of different sorts, of different types. The absorption feature you see starting down there around 1 micron is generally referred to as the 1 micron may facilitate absorption feature, and its location, its depth, many different ways of studying it, but its properties gives us information, we believe, about what the composition of these objects are. These are the rocks that they could be differentiated, fully heated, melted, and differentiated. They could be partially melted. There are a variety of different types of things. It's very analogous to what we see on the Earth with these types of rocks. This column, however, has probably the most, the ones that I'll talk about the most. And the bottom group, which is probably considered to be mostly the C class or C complex types of asteroids, which are generally speaking pretty flat in reflectance. You don't see a lot of detail in this broadband photometry, are the water-bearing objects in the asteroid belt. Most of them are water-bearing, or many of them are water-bearing. This is where we're going to find our samples. So I'm going to talk quickly about evidence for water in these objects. The process that we see in most asteroids, where we're seeing any sort of evidence for water based on spectral collectors, is a process called aqueous alteration. In this case, we define it as rocks that have probably trapped some water or something underneath the rocks, or liquid. The liquid has affected the rocks. This can happen on a time scale of, say, hours to days. It doesn't have years or multiple years or millions of years. It's a very small, short process. If you left something iron in your backyard, you walk out a few days later and it's been pretty rainy, and if you live in Houston like I do, and it's rusty, that's aqueous alteration. And we see this potentially on asteroids. In the asteroids, we see this primarily in low albedo asteroids, the asteroids that don't reflect as much light as some of the others. They're dark. They're the charcoal blue cats of the asteroid belt. And the gold standard for identifying the effects of aqueous alteration or the presence of water in the asteroids is the 3 micron, is located near 3 micron. It's a large absorption feature that's near 3 microns. It's attributed to structural hydroxyl and interlayer adsorb or bound in water in clays. The most recent study, a large study of this that I found was done by Andy Griffin and presented some of the material this year. And he's collected a few hundred spectra at this point of low albedo asteroids, and he's now finding clumps or groups of different types of shapes of this feature. This one really isn't the feature. It's an example of what is not showing much in the way of anything in the way of the 3 micron feature that's tested. The interesting one in this, along with different shapes that he's finding, but the interesting one is this very faint purple one. This is scale has been expanded. This is, reading it correctly, 1999 UP4 or UY4, I'm always, It is a near-Earth asteroid. It is the only one that shows the 3 micron feature. And its shape is similar to what has been more recently identified by spacecraft on the moon. In that the shape of the feature itself, although it is exaggerated in depth here. Also, I hope I get a chance to finish my stuff. We've also noticed that in the visible spectral region, different absorption features, very subtle absorption features that look very similar to what we see in terrestrial polysilicates, in our terrestrial meteorite collection, in the CF2 carbonaceous chondrites, and they're all over the C-class asteroid spectrum. The primary one is this sort of very shallow feature here that's centered near 0.7 microns, and it's called the 0.7 micron feature. And it's largely due to oxidized iron. It's a charge transfer transition between iron, and what has happened is that other investigators, Griffin and Ellen Howell, took a look at the presence of this feature and the correlation of it with the 3 micron feature, which is directly water. This is only oxidized iron, and found that when the 0.3 micron feature is present, or the 0.7 micron feature is present in one of these low albedo asteroids, always indicates a 3 micron feature. It's not always the reverse, but it serves as a delimiter for a lower limit of how many objects could have aqueous alternate products in it or bound water. The other features in this, this is a very small feature, which often gets affected by or fused with the solar G line, that's our astronomers here. But it's potentially a a spin forbidden feature near 0.43 microns, then this whole slope here is a UV blue intervalence charge transfer transition that anything with silicate is going to have this. You see this in the S-class asteroids, but you also see it in the C-class. And there was some direct correlation between the strength of this feature, this color, and the presence of the 3 micron feature. So there are many ways that one can take a look at an asteroid spectrum or spectral data and say, yeah, we're thinking we've got bounded water in this asteroid. But let me add a little bit more of this. Most of the C-complex asteroids that we see with these features are located between about 2.6 and 3.2 astronomical units. That means they dominate the outer part of the main asteroid belt. They aren't in the NDAs. They are largely absent in the NDAs. There's one that I've seen with a 0.7 micron feature. There's one asteroid spectrum that I showed you earlier with a 3 micron feature. And otherwise, we're not seeing a whole lot that are in the NDAs that are there for you to mine for water. So you probably have to stick to comets. The problem with the NEA is that it's going to be hard to observe this feature because thermal infrared will start to interfere with your reflected spectrum near the 3 microns when you get this close to the sun. But the real thought that I would have on this is that no matter what happens, whatever is transporting the objects to the inside the main asteroid belt, where they do dominate, that this population is considered to be about less than 10 million years old, the near-Earth asteroids. All the asteroids that are somehow being moved into the inner Earth group, they only about 1% of them make it. Otherwise, the sun eats them or Jupiter kicks them out. And so it seems to me that perhaps we just have not had an event in the last 10 million years. Quickly, the other major new event has been the evidence for water ice that has been found with another feature center near 3.1 microns by 2 groups at the same time. One, Rick and Emery, finding water ice plus evidence for, this is an expanded version of that, organics. Also, Campines et al. Also found the water ice in the organics. It's published in the same volume of Nature, and is probably the first evidence for direct water ice on an asteroid itself, except for Ceres, which is special, and I'm going to only briefly talk about it here. It seems to have a fair amount of evidence for both water in the form of varying polar ice caps found by Hearn. I probably have the wrong year, but that's definitely. And 3 micron features that could either be due to water or possibly eliminated saponite, but a different volatile. Still, like this alteration does not have the visible absorption features. I forgot to mention that previous asteroid. Vilas does not have the visible absorption features that I presented earlier. And other studies so far that I know of have been inconclusive, but that doesn't mean it isn't being studied heavily by people now. The other thing that people want to look at are heavy metals, which are the concentrated iron and nickel that you might see in an asteroid. Why? Iron is the 9th most dominant or present, 9th most present element within the solar system, and then will dominate it for a while. And you want to potentially mine a concentration of iron and nickel all in one place. So we take a look at the M-complex asteroids. Most of the work being done on them is being done by 2 groups at the moment. One at Ithaca College, one at University of North Dakota. And they've been releasing studies that show that the M-types do have similar features, but also a lot of different types of geological meteoritic interpretations for these features, indicating that they may look like cores, which is what people are hoping for, of course, to metal, with some bits of mantle that are on the surfaces. The canonical M-type in the Psyche is spectrally flat. It doesn't have any absorption feature at all, and the radar has the reflectivity of the metal, and that's all there is to it. In the near-Earth asteroids, there are not many M-types. So let's see. This is a piece of work that I think is very interesting in the last couple of years, where an astronomer has taken a look at radar observations and correlated them with asteroid taxonomic class. And it shows that there's a certain amount of that the mineralogy tends to affect the structural complexity and therefore the radar reflectivity of the object. class near-Earth asteroids have a reflectivity that's comparable to main belt asteroids, and this, they suggest, is the strength of metal resisting any sort of generation of regolith in many ways. Here's my cautionary notes. That the object 2008 TC3 was an asteroid that came into the Earth. We had 19 hours worth of warning. It was identified, it impacted the Sudan 19 hours later. Telescopes madly turned and tried to observe it, and they did get a very crude, of course, it's moving fast and very faint, crude reflected spectrum of this object. But it looks like kind of one of those flat C-class and C-complex asteroids. And laboratory spectra of the meteorite that when meteorites are recovered looks very similar. Those meteorites were recovered within a week. You wouldn't expect there was much degradation, and it turns out that the composition is entirely different. So when you see a spectrum of an asteroid that we have acquired, don't necessarily assume that we know all about it and that it's the same as what it is. Same thing for the second example of this is Phoebe, ground-based. Maybe there's a coincidence in my practice because that's the asteroid to show it, and Phoebe has returned from Cassini remote sensing. Much more detailed, many volatiles, much more compositional evidence as you get closer to the object. What's their structure? Seen some of these before, I think, today. Other asteroids, they're sort of smoother, they have craters, they're small, that stack goes out at the bottom here. Same thing for Deimos, Phobos, and Castor, which is in the previous one. And then you get Ichikawa, which is maybe 600, a little bit less than 600 meters in length. That's north down. And it looks all the world like the canonical orbital pile, which has been discussed. And with the gravitational lows, where the smaller particles, and they were particles, went to those particular locations. So they do exist as orbital piles. We do have ground-based techniques that predicted the roughness of this object was going to be much more so than we would have expected. And that is a confirmation that in fact it can be electric, but not always. This is just information about Itokawa. And I'm going to close with a quote that a man, a scientist named Andre Brahe, said after the Voyager mission went past Saturn for the first time, and we saw that there weren't 3 rings, but in fact multiple ones. And his comment was, there's more diversity in the solar system than there is in the brains of bright theorists. And I would agree, and I would caution everybody to bear that in mind when they make assumptions about what it is that we are and are not.